Hello everyone, thanks for your attention on our work, FairNN, Conjoint Learning of Fair Representations for Fair Decisions. This work is in the cooperation with Tongxin, Zhang, and my supervisor Professor Bodo Rosenhahn from Institut für Informationsverarbeitung, Leibniz Universität Hannover, und Vasileios Iosifidis and Professor Eirini from the L3S Research Center, and Professor Michael Yang from Faculty at ITC, University of Twente, the Netherlands. This work is included in the 4V bias project. Nowadays, supervised learning methods are suffering from the bias problems in the collected dataset. The bias data will lead the training model to make biased or discriminative decisions. For example here, the training model made different decisions for two applicants who have the same qualifications. The only difference is that the rejected one is a female. This is unfair. The model makes this unfair decision because the data set used for training has strong bias in the gender attribute. The goal of this work is to reduce the negative effect from the data bias. Some attributes, such as gender, nation, should not affect the model to make unfair decisions. To achieve this goal, we propose a framework named FairNN, and here is an overview. It consists of three parts: an encoder, a decoder, and a classifier. The auto-encoder is trained to learn representation, and the classifier is trained to make fair decisions based on the features given by the encoder. We add a KL-Divergence constraint to force the auto-encoder learn fair representation. The loss function of the classifier is tweaked towards fairness through the equalized odds regularization. We will analyze each part of the framework in details. This is the structure of our auto-encoder. The encoder learns an intermediate representation for the given data, and the decoder reconstructs the data from the learned intermediate representation. The loss function to train the autoencoder consists of a reconstruction loss and a KL-Divergence regularization. To make the decoder have better reconstruction ability, we use mean square error loss associated with a cross entropy for each attribute. The MSE loss only encourages the output to have small overall error compared with the input data. The cross entropy minimizes the reconstruction error of each attribute. The KL-Divergence constrains the length features of the protected and non-protected groups to have similar distribution properties. There is strong bias in the dataset, which makes the model lose this information more important than others. A solution to reduce this effect is to mix this kind of information with others. In this work, we hope the model treats the protected and non-protected groups equally, so we introduce the KL-Divergence to encourage the encoder to learn the representation, in which the representation of protected and non-protected groups have a similar distribution. As shown in this example, the points can be distinguished easily between the females and males in the original input. After being encoded by our methods, these data points and the gender attribute are mixed. Our goal is not only having high classification accuracy, but also not losing fairness, which is the main goal of this work. For this purpose, we add an equalized odds regularization term to train the classifier. Here, the theta FPR and the FNR are the difference of false positive and false negative rates respectively. Equalized odds is used to minimize both the difference. We evaluate our method on two real-world datasets, adult census income dataset and bank marketing dataset. The task in adult census income dataset is to predict whether a person's income is over $50,000 a year, and the task in a bond marketing dataset is to predict whether a client will make a deposit subscription. The evaluation metrics include accuracy and balance accuracy for classification and equalized odds for fairness performance. These two diagrams show the performance of different methods in different evaluation metrics on the two datasets. We can see that our methods reports the competitive classification performance, but has better equalized odds scores, i.e. the fairness performance. Here, we conduct Ablation Study to judge the effectiveness of each part of our method. Larger alpha indicates more KL-Divergence Regularization, and larger beta means higher equalized odds constraints. We can see that these two regularization terms do not affect the classification accuracy, but significantly improve the fairness performance, i.e. equalized odds, and also improves the balance accuracy. To better understand what kind of features are learned from the autoencoder part, we visualize the extracted features. The left one illustrates that the protected attributes information is mixed up in the latent space, which indicates that the fair representation is learned. The right one shows that the label information is distinguishable from the learned fair representation. The learned representation is not only fair, but also suitable for the classification task. Here, we show the difference during training process between the left one that use MSE loss and cross-entropy loss, and the right one that only use MSE loss. We can see that the left one does not only report better performance, but its training process converges faster. Finally, we made a conclusion to this work. We propose an autoencoder-based framework for fairness-aware learning. To enforce the autoencoder to learn fair representation, we use KL-Divergence to regularize the training. To encourage the classifier to make fair decisions, we use equalized odds to constrain its training process. The code helps reproduce our experiment is publicly available. Welcome to download and play it around to know more about our idea. This work is supported by BIOS project. It is a project funded by the Volkswagen Foundation. Thanks for your attention and welcome your question.